se barre. Le temps nous rattrapera et nous fera changer.
Complete?
Oh, mute.
Okay, so let's get started. So today we are going to continue to learn about data modeling and databases. So just a quick recap about where we are so far in this course. So I think we spent the last couple of weeks to talk about how to organize our data into relational model, right? So our view is you can actually organize your data into a whole bunch of things like tables, right? And then how to query them. We talk about different query languages. So essentially the thing that we have been talking about so far is you have a database system, and then you as a user have something you want to do about your data. And underneath the cover what the database system interact with is your hard drive, is your memory. You can start to create relations inside database, for example, by the SQL query. And what's going to happen is the database is going to actually create a table for you on the hard drive. You can put data in, you can manipulate data, and you can actually write SQL queries to query your data. So the moment you write a SQL query that looks like this, what's going to happen is the database is going to bring the data all the way from the hard drive to the main memory and back to you as a user. The goal of the database system, when we say it's actually declarative, is that the database system try to deal with everything on the left-hand side, such that you as a user do not need to think about how the database actually get the answer for you. So all you need to do is to specify what kind of information you want from the database. So starting from this lecture, we are going to assume you already know about this process. We talk about different query languages, and we talk about how to write SQL queries, and we spend 2 lectures actually write SQL queries together. So starting from this lecture, we are going to assume you know all of this. You know relational algebra, you know relational calculus, right? You know different subsets of SQL queries, and you actually practiced by yourself, right, in the last week, and also continue to practice for the rest of the semester, right? So just some quick learning resources, right? So everything about SQL is actually in these 3 different chapters. We assume you will do a deep read in all these chapters because it's very hard to replace them by just watching lectures. There's the hands-on session recordings and the SQL query on our website, right? So watch them and practice those like all by yourself, right? To make sure you actually write some SQL queries. There's 3 additional Katacoda tutorial. They are actually very similar to what we have in the hands-on session, right? You can actually go through them and play with them, right? To make sure you are familiar with the ecosystem, familiar with how to write SQL queries. So we continue to have exercise sessions. There's actually multiple SQL exercises, right? So attend them and try to think about those queries. But again, we are talking about a kind of program language, right? So the best way to actually learn about those is to practice. I hope we know a better way to replace all the practices, but unfortunately we don't, right? So just practice, practice, and practice. But starting from this lecture, we will assume you go through all the practices. We'll assume you already know how to write SQL queries. We are going to switch gear and to talk about, okay, now you know how to manipulate your data, right? How to query the data, how to manipulate data. We will talk about now you want to build a real world application, And how can we actually make that happen? What is the process to actually use all the SQL queries that you already know how to write so far to actually try to build real applications? So of course, our goal is not to build a specific real world application, but we want to understand what are the right way to actually think about the process of building any application that you will see in real world. So essentially, we will focus on the principles of how to use database to implement real applications, about the principles about how to design the database schema, because there are so many different ways you can design different type of schema to encode the same piece of information, and how to reason about the property given a design of the schema. So in this lecture, we will start the discussion about this. We are going to talk about first an overview about how people are building those kind of database applications in real world, containing 3 different phases, including conceptual modeling, logical modeling, and physical modeling. And we are going to talk about each of those phases and what they are actually doing. And then we are going to go deep into the first phase of building building database applications, which is called conceptual modeling. And we are going to talk about how to do that using something called entity relationship model. Okay, so the process that we are interested in take as input a real world application that you want to build into and output a physical implementation using your database system. And usually we think about this process as something contains 3 different phases. The first phase is called conceptual modeling. So that is the phase that actually interact with the real world. So what you are going to do as a designer of the application in the conceptual modeling phase is to observe the real world, think about the information you want to encode inside your database application, and try to capture the domain to be represented. Essentially, that's provide one abstraction about the real world. And in the second phase, that is something that we call logical modeling. You are going to take as input this conceptual model of the real world and try to map those concepts into concrete logical representation. So here by logical representation, what we have in mind is actually your relational model. This is the part that you take as input everything you want to model in the real world and map them into concrete relational model scheme. And then the third phase is called physical modeling. And that is a phase that you are going to take as input this logical representation, which is your schema, and try to implement them in concrete hardware. And hopefully, most of the job in the third phase, which is physical modeling, is going to be automatically dealt with by the database for you. Now let's look at a concrete example. Let's go back to this very first application that we went through together in the first lecture. Assume you want to build a very simple view of management system, right? So what can we do, right? So in this application, we look at this application, right? So what do we have in this application? What are the data that we want to capture in this application? Well, there's a whole bunch of, entities, a whole bunch of things, right? So there's a different product, and each product contains different parts, right? And each part has a whole bunch of attributes. By looking at this application, right, you can actually write down all the information that you want to capture in natural language, in English, for example, right? So we have a whole bunch of product. Each product has a name. Each product contains a set of parts, right? A part has a name, a part has a cost, a total cost, so on and so forth. You are able to write down what you want to capture in natural language. But of course, this is not enough for building computer applications because the machine doesn't really understand what you're talking about. So the first phase of modeling this application is really try to translate all those requirements in natural language into something that the machine can understand, and also into something that you can communicate to other people in a very precise way. So essentially, in the first phase, what we are going to do, as we will see how to do it in this lecture, is really take as input that long list of requirements that you are able to express in natural language and translate them into a visual diagram that look like this. So after this lecture, you are able to actually read about this diagram to understand what people want to build in this application. But intuitively, if you look at this diagram, right, you can already get some sense about what we are talking about. So there are two different entities, there's product and this part, right? In this application, they participate in some of the relationships called has. If you look at the part kind of rectangle, you'll see, yeah, it's associated with a name, with ID, with quantity, so on and so forth. Intuitively, this is just a precise visual representation of what you want to build inside this application. So, and the second part in the modeling journey is actually take as input this visual representation of your application and map them into a concrete relational model. So there are different ways that you can actually do this mapping, and we are going to talk about how to think about them and how to do them in the coming Wednesday. But intuitively, right, if you take this conceptual model on the left-hand side, one way to map them into a relational model is to, for example, store all the part into a part relation, store all the product into a product relation, and store the relationship into another relation contains the product ID and the part ID, for example. So we call this step logical modeling because it maps the conceptual model into a concrete logical data model. And the third phase is called physical modeling, right? So in this phase, we hope most of this is actually done by the database system for you. So essentially in this phase, you are going to take as input your logical model, which is a relational model, and try to map them into some physical implementation or representation on your hard drive. Essentially, you're going to take as input this logical model and try to map them into a sequence of 0 and 1s, right, on your hard drive. Hopefully, this can be done by you issuing SQL query to the database system, and the database system implement that for you automatically. So this is the three different phases of building a real-world application, and at least how to think about building a real-world application. In this lecture, we are going to focus on the first phase, that is conceptual modeling. So what are we trying to do in this phase? In this phase, what we are actually trying to do is to take as input your real-world application, which is very complex. There are so many details you could model. There are so many pieces of data there. To really try to summarize it and provide one abstraction for all your downstream process. The goal is really try to observe the real world, think about the application you want to build, and summarize them into a mini world, right? Which is simplified, but hopefully rich enough in terms of functionality for your application. And given that mini world, you can describe that using a conceptual schema. We are going to talk about one specific way of describing that. And then given that schema, you can actually do the logical mapping often in automatic way. So before we talk about the concrete ways of modeling things, right? So let's think about what do we mean by modeling, right? So why do you use the word modeling, and what do we mean by a model? So if you recall, a couple lectures ago when we talk about relational model, right? So we introduced something called a key constraint, right? So if you think about what the key constraint trying to do, is actually specify all database instances that are valid or allowed in your database schema. It's tell you, if you give me a piece of data, whether that is allowed inside database or not. So conceptual modeling actually try to do something very similar. So as we are going to see, it specifies actually all the database instances that is valid or allowed inside your application. So when we talk about the modeling, right, we are actually trying to introduce all those type of constraints to make sure we know what data is possible or allowed inside this application. So you will see this point really soon when we talk about something called cardinality. Okay, how should we think about conceptual modeling? So there's so many different ways to do it. In this course, we are going to focus on a very specific way for you to do that. And the thing that we are going to talk about is something called entity relationship model. Essentially, this model is one application with 3 different element types. So there are entities inside your applications, which are the things that you want to put into your database, right? So, and we have multiple of those entity sets, right? Each entity set contains a set of similar entities, for example, all the students, all the professors, for example, and each entity corresponding to an object in the real world, which can be distinguished from other objects, right? And when we talk about similar, right, like an entity set is similar, right? So a set of similar entities, when we talk about similar, they mean actually entities in the same entity set, they will share the same collection of attributes, right? Intuitively, they are the thing that is able to be put inside one relation. So for example, if you think professor is an entity set, right? It actually contains a set of similar entities, each entity corresponding to a single professor, right? Why they similar is because they share the same collection of attributes. They all have names, they all have office, they all teach lectures, for example. And if you're familiar with object-oriented programming, right? So the thing that we are talking about here, entity set, is kind of similar to a class, right? In, for example, in the Java programming language. And the entity, right, which is kind of an instance of an entity set, is very similar to an object, right, in Java. So, but the only difference is when we talk about the entity relationship model, it is actually a data model. It doesn't have functions, doesn't have associated method associated with that class. So that's kind of one slight difference. When we are talking about a data model. And then the second element type in entity relationship model are attributes. So they are actually those attributes associated with each of those entities. For example, if you have an entity set called a professor, right? So you can say, yeah, so all the entities here are going to be associated with a whole bunch of attributes, for example, the ID or the name. And then there's another element type in entity relationship model called relationships, which are just things that connect multiple entity sets. For example, you could have relationship between professor and lecturer, saying, this professor is teaching this lecture. You could have relationship between students, which is the entity set, and lecturer, which is another entity set, saying that, okay, students are going to take lectures, for example. So when we talk about entity relationship model, right? So there's a specific way for you to actually represent your model, which is by drawing an entity relationship diagram, which is a graphical way of representing entities and relationships among them. So it's actually very simple to actually draw. So if you have some entity sets in your application, and you know which collection of attributes are associated with this entity set, the thing that you can do is to actually draw one of this rectangle and put the name of the entity set in the middle, and then you can represent, okay, I have this entity set in my application, and then you can write a circle, and each one of them corresponding to one potential attribute, and you can connect them, right? You draw a line between this rectangle and this circle, you say, yeah, and this entity set is associated with this attribute. So by drawing this, you are actually telling people, or telling the machine, or telling your friend, okay, I have an application. In this application, I have one entity set with this name, for example, professor, and then I have multiple attributes associated with this entity set. So let's look at one concrete example, right? Assuming you are building one application with a whole bunch of people, right? So one thing you can do is to say, okay, I have one entity set called a person, okay? Every single object in this entity set is a person. So, and I have a whole bunch of attributes associated with this entity set. For example, your national ID, your passport number, and your name, for example, right? So this defines one entity set associated with 3 different attributes. Once you have multiple of those entity sites, right, you can introduce relationships among them. For example, like the way to do that is to say, yeah, here's, for example, two entity sites participate in one relationship. You can write, you can draw this kind of diamond shape, right, and put a name inside the diamond shape, right, and then connect these two entity sets. So by doing this, you are essentially saying, okay, I have two entity sites in my application. And in this application, these two entity sites are going to participate in this relationship. For example, if you have the person entity sites, you have a whole bunch of people inside your application. You have another entity site, for example, called lecture, which have an attribute associated that called ID, for example. You can say, yeah, I mean, this person can teach that lecture. I mean, there's a relationship between people and lecture. The thing you can do is to have one relationship, for example, called teach, and connect these two entity sites, person and lecture. You could have, for example, another relationship. For example, say, yeah, I mean, people can also take lecture, right? Not only teaching them. You can say, yeah, here's another relationship called takes, also connecting lecture and person. So it's a very simple way for to describe all the entities that you have in your application and what type of relationships you are modeling inside this application. So similar to relation, like similar to relational model, you also have the notion of keys, right? So in this case, not all the attributes associated with entity site are the same. Some of them are kind of special. So we can define a key as the minimal set of attributes. Key is a set of attributes, not a single attribute, right? So a minimal set of attributes whose value uniquely identify an entity in the site. For example, you can say, yeah, national ID uniquely identify a person in the sense that if you tell me this national ID, I can tell you a specific person in this entity site. So if you're able to do that, what you are actually saying is national ID as a set of attributes, right? Which is set contains only one element. This national ID is the unique identifier for entities in this entity site. So potentially it could be your primary key, right? You could have other collection of attributes that can be keys, right? For example, you say, yeah, I mean, passport number, right, could be another unique identifier for a person, right, in this entity site, right? You can say, yeah, passport potentially can also be the primary key, right? So there could be multiple of those candidates, right? Each one of them is a unique identifier, right? So, and all of them are called candidate key, right? Because they're candidates for the key that you can use to identify an entity in the sites. And only one is called the primary key, right? That's kind of the primary identifier that you are going to use. So the way to represent that is by just underlining it, right? For example, if you say, yeah, so in this application, there could be multiple ways for me to identify a person. I could use national ID, I could use passport number, right? But I choose the primary key as my national ID. Okay, and you can just underline it under the national ID to specify that. So, but there could be like other choices. So, which candidate key should be used as a primary key, and what would be the implication of picking a subset of attributes as primary key, right? So let's look at this one application, right? One example. That is, assuming I have entity site person, I have national ID, I have passport number, I have nationality, I have name, right, associated with the person. Assuming I say, okay, nationality and the passport together form the primary key, right? So is that okay? And the answer to that is actually depends, right? So it actually depends on what application that you are actually trying to build, and also what the assumption you are having on the data. So now let's assume the world that you live in is actually the real universe we are living in at this moment, right? Where the passport number look like something like this, right? So if you are assuming the passport number look like what you have in real world, then picking these two attributes together as a primary key is actually not okay, because if you look at the passport number, it's already encode nationality. Right? Like by just reading the passport number, you are able to extract information about personality, which actually means that this combination, right? So which is nationality and passport number is not the minimal set of attributes forming a unique identifier, because they are not minimal, right? You are able to remove the nationality from this set of attributes, and you still are able to identify a person because the passport number contains information about nationality, right? So if that's the assumption about passport number, then this combination, nationality and passport number, is not really a candidate key because it's not minimal. But again, if you are assuming in your application, right, passport number does not include nationality information, then this combination could be a valid key, right? So it all depends on what application you are building and what you are what are the assumptions you are having in this application. So let's look at another example, right? So assuming you have, like the same entity site and same collection of attributes, and I say, so I want to have in this application, national ID is the primary key, right? So what about one person have, for example, like two citizenship, right? Belongs have two nationality, for example, right? Then potentially this person can have essentially two different national IDs, right? So in this case, it's actually very important that the entity relationship diagram you are drawing, right, is your assumption, your model on your application, right? It doesn't tell you things that you didn't model like inside this application, right? So if you cite this national ID as a primary key, what you are saying is in this application, I'm assuming if you give me a national ID, I can identify a person unique way, like in a unique way, right? If there are other cases, right, so that actually break this assumption, what you are saying by drawing this ER diagram is I'm not going to consider those, okay? The entity relationship diagram is the collection of assumptions that you are making on your data, right? It reflects the assumption that you have. So if your application, right, all person come from a single country, then this is a pretty good model, right? However, if in your application that this is not true, right, so then this is probably not a good model, right? So whether a model is good or bad, right, actually depends on what application you are building and how much your model actually reflects reality. So there's no universally good way to judge whether a certain attribute is a good key or not, right? So that all depends on your application. So another thing that could be interesting to talk about is now we have different candidate keys, right? So how can I pick the best key, the best candidate key to use as my primary key, right? So, and again, it depends on applications, but there are some principles, right? For example, not all candidate keys can be good primary key, right? So there could be some attributes that you can use to uniquely identify an entity site, but probably don't want to use them as your primary key. So here's one very extreme example, right? So you could say, yeah, for every single person, I have another attribute, which is the current position of that person on Earth, right? So it's a three-dimensional space, right? So every single one of us occupy a unique position at any time point. So that's unique, right? So given the current time point, if you tell me, yeah, this position on Earth, I can identify a person, right? So it's a unique identifier. In principle, I could use that as a primary key, but what could be the potential problem, right? So the potential problem is the current position on Earth for every single person keeps changing, right? So people keep moving, so this attribute, the value of this attribute keeps changing. even though you can actually uniquely identify a person, yeah, so because this attribute keeps changing, in most of the applications, you might not want to use this as an identifier, because then the identifier for the person actually keeps changing, and it's very hard to actually get them right inside your database. So that's some general principle about what is a good permit key and what is a bad permit key, right? So good permit key hopefully would be stable and would be something that is easier to assign and easier to get. But of course, it's not really absolute criteria, because it all depends on your application. But in this extreme case, right? So I hope we can agree. Yeah, maybe national ID is a better permit key for to use inside your application. So another thing that we have in entity relationship diagram is something called a role, right? So that's going to be useful when you have, for example, one entity site, for example, person, right? And you have relationships connecting essentially the same entity sites. So for example, you have the person entity site, you can have a relationship called parent of, right? So this parent of relationship like connects two entity sites, but they're the same entity site, because like both participants of this relationship are person, right? So in this case, we need some way to distinguish this participation, right? You can actually put the name of the role here. For example, here you say, yeah, this parent of relationship connecting two entity sites, but both entity sites are person, right? But one of the person plays the role of a child, another person plays the role of a parent. And then you can actually distinguish the participation of the same entity site in this relationship. So in this case, yeah, so this is what you can do. This is pretty much all the pieces that we have in entity relationship model. We talk about entity site, attribute, relationship, we talk about the key, we talk about role. We can already use these concepts to model something, right? So we have been talking about this university schema in the last couple of lectures, right? So let's try to read this diagram together. So let's try to start from the left-hand side, okay? If you look at this entity relationship diagram, yeah, so the first thing we can see is, okay, what are all the entity sites that we have in this application, right? So in this case, right, we have 4 different entity sites. We have students, right? And for students, there are 3 different attributes associated with students, right? We have ID, we have name, we have semester, for example. We have another entity site called lecture, which have ID, has credit point, has title, has 3 different attributes associated with lecture. And we have another collection of entities, which are professors, right? With 4 different attributes associated with the professor, with a personnel number, name, room, level, and then there are teaching assistants, right, associated with 3 different attributes. So essentially, yeah, we have 4 different types of entities in this application. And then they participate in different relationships. For example, you can say, yeah, so there's a relationship attends between the student entity site and the lecture entity site, right? Student attends lecture. So there is the gives relationship between lecturer and professor, right? Professor gives lecture. And within lecture, right? So there are some of them are the prerequisite of another lecture, right? So you have another relationship requires, right? Connecting 2 entity sites, but they're the same, they're both lecture entity site. So one lecture plays the role of prerequisite, another lecture plays the role of the follow-up lecture. Right? If you remember in the previous couple lectures, right? Like 3 lectures ago when we talked about recursion, right? So we have that relation, right? Contains 2 different attributes. One is prerequisite, another is follow-up, right? Intuitively, this requires relationship models that essentially are saying, yeah, so the 2 lectures participate in one relation called requires, One has the role prerequisite, another have the role follow up. And you can say, yeah, a teaching assistant works with professor, right? So essentially, every single participation in this relationship has one assistant entity, have another professor entity. And you could have relationships connecting, for example, multiple entity sites, right? Like more than 2 entity sites. For example, you have this test relationship connecting 3 different entity sites, connecting students, connecting lecturer, connecting professor, right? So in this case, you are saying, yeah, this relationship is not binary, right? Because I have more than 2 participants, right? So for every single relationship here, I have 1 student, 1 lecturer, and 1 professor, right? Students take the test of this lecture provided by that professor, right? That's one instance of this relationship. And you can also put attributes, right, to relationship, right? So in this case, it means that for every single participation of this relationship, in this case, it's a triple: student, lecturer, professor. I can associate that with an attribute, right? In this case, for every single of that triple, I have an additional attribute associated with that, which is a grade of the test the student take. Right? So if you look at this, this really tells you the assumption that I have on my data that I want to put into this application. Right? So this is why it's very important for you to do conceptual modeling, because after that step, we are on the same page about what are the data that we are going to have here. So there are many cases in entity relationship diagram that could become a little bit tricky, right? Now let's look at these 2 different diagrams, right? On the left-hand side, I have one relationship test connecting 3 different entity sites: student, lecturer, and professor, and I have another relationship games connecting lecturer and professor. And look at the diagram on the right-hand side, right? The only difference is, oh, my test relationship does not connect professor anymore. It only connects students and lecturer. What are the differences between these 2 different models? Right? Which one is a good model? Which one is better, right? So I mean, in this case, right, in general, there's no universally good model, like a better model than the other, right? It all depends on whether they really reflect the real world or whether they reflect the application that you want to build. If you look at these 2 diagrams, they actually try to tell different things. They're actually modeling different applications, exposing different assumptions on your application. So on the left-hand side, it means that for every single test that the student takes, it's very important in this application for you to know which professor, for example, provide that test. Okay, every single participation in the test relationship is the triple. On the right-hand side, right? So essentially, you are saying in this application, I don't really care which professor provide that test. All I want to encode in this application, which student takes the test of which lecture, and which professor gives which lecture, right? So in the diagram on the right-hand side, for every single test between the student and lecturer, you actually do not know which professor can provide that test. So which one is better? I mean, I don't know, right? So that depends on in your application, whether it is important for you to encode the professor who's giving that test for specific lecture, right? So for example, you can live in a universe that if a professor is giving certain lecture, then that professor is providing certain test, right? If you live in that universe, right, you do not need to associate that professor with a test because you can already infer that from which professor is giving which lecture. Right? In that case, maybe the one on the right-hand side is a better model. Right? But for example, if you cannot do that, right, a professor can teach certain lecture and a different professor can give a test, right? In that case, maybe the diagram on the left-hand side is a better model, right? So again, which model is better depends on your application, but very important for you to be able to look at the diagram and try to read out the assumptions that people are having in this application. In that case, right, so like on the left-hand side, every single participation in the test relationship connect 3 different entities. On the right-hand side, every single participation in the test relationship connects 2 different entities. And another thing that we need to be really careful about is when we talk about the entity relationship diagram, it tells us the assumptions that we are making about our application. On the other hand, it also tells us the assumptions that we are not making in this application, because they are the things that we are not drawing in this diagram, right? No matter how natural it is, a diagram doesn't contain things that you do not draw. For example, by reading this diagram, there are information that we cannot extract from this diagram. For example, whether 2 students are friends or not, we don't know, right? Because we don't have this relationship friends between 2 different students. We don't know which assistant kind of which teaching assistant participate in which lecture, because we don't have that correspondence between assistant and lecturer, right? We don't know how many lecture each professor can teach, because that's simply not in this model. So those are the things that you cannot read out of this diagram, right? No matter how natural that looks like, right? Yeah, sure. I mean, there should be a friends like relationship between 2 students, right? Because why not? But no matter how natural that thing is, if you do not draw it in this diagram, right? That are the information that you cannot really extract from this model. The model is always a simplification of the real world application, right? So it tells you what you are assuming and also tell you what you are not assuming in this application. Now let's look at some slightly trickier cases. So one tricky case is multi-way relationship can be tricky. So if you look at these 2 different diagrams, right, they are actually modeling different things. So on the left-hand side, I have this suggest relationship connecting 3 different entity sets. So assume that by that, I mean a professor teach a course and also suggest a textbook for this course. Okay. On the right-hand side, right, so I could have these 2 binary relationships connecting these 3 different entities. I could have the suggest relationship, say, yeah, professor suggests a textbook. I have the used in relationship saying, yeah, so this textbook is used in that course. If you put these 2 side by side and try to understand what are the differences, right? So it could become a little bit tricky, right? So here, one difference is if you look at the diagram on the right-hand side, right? Essentially, you could have the cases that the professor suggests textbook, but that textbook has never been used in any of the courses, right? So that is possible on the right-hand side. But that's not actually possible in the left-hand side. In the left-hand side, if professor suggests a textbook, you must have the course associated with that relationship, because it's always a multi-way relationship. You have professor, textbook, and the course. You never have the case that professor suggests a textbook, but there's no course associated with that textbook, right? So that's the difference between, I mean, that's one of the differences between these 2 different diagrams. And you could have different ways of arranging this kind of binary relationships, and you actually have different type of differences, right? For example, on the left-hand side, I have the same multi-way relationship. On the right-hand side, I have professor suggest textbook. I have professor teach course, right? So like in this case, right, on the right-hand side, it's also kind of encode a different type of data compared with what you have on the left-hand side, right? So in this case, the professor suggests textbook, professor teach courses, right? But professor on the right hand, the professor can actually suggest a textbook for a course that the professor does not teach, right? So that is possible for your model on the right-hand side, but that's not really possible for the model on the left-hand side, right? So this is kind of one difference between a multi-way relationship and a multiple binary relationship between entities. So again, you can arrange this in different ways, right? So if you look at these two different models, right? On the right-hand side, you have professor teach course use textbook, right? So here again, you are actually missing some of the information, some of the association that you could have on the left-hand side, right? So in this case, professor can teach a course can use a textbook, but professor might not like that textbook at all, right? For example. So you can also connect them in different ways, right? Have this text using course, right? In this case, in case we'll see later, it's not. Let's add to very interesting relationship. The diagram, how can I test whether they can say they are in co-game? So I'm talk about. Let's take a break. If any questions, just raise me here to answer your question. But otherwise, let's break in 15 minutes. Okay, so let's continue. Yeah, so here we are looking at two different entity relationship diagram, right? So one thing that we want to understand is, okay, are they equivalent? So we are going to introduce some precise way about test it, right? But before that, let's just look at this two diagram and see what's their difference, right? So on one hand, you have a kind of one three-way relationship suggest between professor and course and textbook, right? On the right-hand side, you actually have four different entity sets. You have professor, course, and textbook, but you also have another entity set called recommendation, right? And each recommendation, right, can be associated with a professor, with a course, and with a textbook, right? So are they equivalent? So I mean, when we talk about equivalent, what do we mean? We mean that whether kind of a database modeled by the model on the left-hand side can be modeled by the right-hand side and vice versa, right? So that's what we mean. So we are going to introduce some very precise way for you to test whether these two things are equivalent or not. But right now, right, so on the left-hand side, so you always have a professor, course, and the textbook together because it's a three-way relationship. You cannot miss any of those, right? But on the right-hand side, you could have, for example, some recommendation R is associated with a professor, associated with a course, but that's not associated with a textbook, right? So that could happen in the model on the right-hand side. And in this case, right, so clearly they are actually not equivalent, right? So that's one counterexample about that. So essentially, as you look at this, a multi-way relationship is kind of very hard to be replaced by a collection of binary relationships, right? So sometimes it's fun. I mean, sometimes maybe in your application, you don't really care about this small difference between these two things. But when we talk about whether they're equivalent or not, right? So that's something to be careful about. So inspired by this example, right? So if I have two diagrams and ask you whether they're equivalent or not, what has a systematic way for us to test it, right? Should we always try to find these counterexamples in a more or less ad hoc way, or whether we can actually have some really precise, systematic, and principled way of testing their equivalence? So that actually goes to one thing that's actually like a couple of years ago when we teach the course, we actually do not have this formal semantic of entity relationship diagram. We just introduce what you just saw so far, right? So, but the one thing that we realize is if you only teach you guys this graphical way of modeling your data, many people will think that it's inherently very vague and imprecise because all you have is you're drawing a whole bunch of things on a piece of paper. So, but that's not true, right? So what's actually important is to realize the entity relationship diagram is a very, very precise and formal language, right? And to make that point, right, we are going to talk about the formal semantics of the entity relationship diagram. When you draw that diagram on a piece of paper, what are you actually trying to formally say to the rest of the world? So essentially, right, the way to think about its formal semantic is to go back to what it is. It's a modern language, right? So it defines the set of database instances that it allows in your application. And all we need to do is to actually define such a mapping. That is, if you give me an entity relationship diagram, what are the database instances? What is the set of database instances it allows in your application in a precise way? And that's actually not that hard to define. So here's a formal semantic. So essentially, a diagram, right? So it's an instance of a constraint language. It defines a set of database instances. So we have all the possible values you can take in your database instance. So in this case, we use D as the domain, right? So that's all the possible values you can take. So there are two different types of values that your database can have. So there are those concrete values, we call them B, right? They are concrete values, they are integer, string, floating points. They are the concrete things you can put into the database. And then there are those abstract values, and we call them delta. So they are the abstract things corresponding to an entity. For example, one professor, right? So that's one entity in that entity site. right? And we call that an abstract value that corresponds to entity, not correspond to any concrete things like an integer, okay? So, and once you have this, you can actually define such a mapping between the scene you draw and the concrete logic sentence about the assumptions you have in for your application. For example, whenever you have an entity site E, right? So that can be translated into a predicate. Here we assume it's the same name E, right? Which is actually saying, yeah, so this abstract value X is of the type of this entity site, right? And then every single attribute that you draw, right, become a binary predicate associating an abstract value X with a concrete value Y. I say, yeah, so this entity have this attribute. And then every single relationship, for example, with n different participants, right, become another logical predicate, right, with n different argument, right? So here you have R like this relationship R, right, become the predicate R, has n different participants, x1 to xn, right? And then each of this xi corresponding to some entity, right? So once you do this translation, right, what are the database instances that you allow inside this model? Essentially, that's all the possible first order interpretation of this logical system, right? What is the interpretation of the predicate of an entity site, right? So that's all the like possible subset of this abstract value, right? So what is the interpretation of this binary predicate, right? So that's all the possible pairs between the abstract value and also the concrete value, and that's a pair, right? So this abstract entity have that attribute, right? And what would be the first order interpretation of these different relationships, right? So they are the subset of the cross product of the abstract value. So, and essentially, if you look at entity relationship diagram, right, each of those subgraph, they actually give you a first order logic sentence. For example, if you have this subgraph, you have two entity sites, you have one relationship connecting these two entity sites. So essentially, formally, what you are seeing by drawing this thing is actually this sentence. That is, if I give you two abstract entities, right, x1 and x2, if x1 and x2 participate in this relationship R, right, it actually implies that x1 have the type E1, right? X1 is of entity set E1 and x2 is of entity set E2, right? So by drawing this subgraph, what you are seeing is essentially this logical sentence, which give you something very similar to a type constraint, right? You cannot put in this relationship R a different type of entity sites. So fundamentally speaking, this is what you are trying to convey by drawing this subgraph. Essentially, it tells you a valid database instances for your application should satisfy that if you have x1, x2 participate in this R, right? x1 need to be of this type and x2 need to be of that type. So essentially, relationship, you can think about that as something similar to a type constraint. And whenever you draw something like this, you have entity site connecting to an attribute, right? So fundamentally speaking, right? So formally, you are actually telling this sentence to the rest of the world. That is, if you give me X, as long as X is of the type E, right? X belongs to that entity site E. It actually implies there uniquely exists a value Y, which is like concrete value, such that the X is associated with Y, the AXY is true, right? So whenever you have this subgraph, this is the logical sentence that you are saying. This actually tell you for any valid database instances under this ER model, it should satisfy that as long as X is of the type E, then it can be uniquely associated with concrete value y, right? This is very precisely what you are trying to say. So let's look at one example, right? If we take this diagram, you have three different entity sites. There's a one three-way relationship connecting these three different entity sites, and the professor has the attribute name, right? What do I mean by this diagram, right? So underneath the cover, what you are saying is, okay, I have one sentence saying that if you give me a professor P, right, as long as this P is a professor, I can uniquely associate that with a name, okay? And this name is a string, okay, for example. And then for this three-way relationship, it's actually give you a type constraint. That is, if you give me three different objects, P, C, and T, that participate in this suggest relationship, then I must have P is a professor, C is a course, and T is a textbook. So these two logical sentences is actually what this diagram try to tell you. So if you take this view, right? So, and we go back to our example about this multi-way relationship, right? It's not that tricky anymore, right? Because to understand what database instance is allowed under each of this ER model, all you need to do is to really try to think what are the formal logical formulas I'm specifying by drawing that diagram, right? And how can I check the equivalency between two ER diagrams? It's very simple, right? So on like you have diagram one, you translate that into a whole bunch of first order logical sentences. You have diagram two, you translate that into another collection of logical sentences, and you try to see whether they're equivalent or not. That is something not that easy to do, but at least that's something very systematic and the principle, right? So for example, if you have this diagram, right, what are you trying to specify by drawing this? And you have the thing on the right-hand side, right? So what are you really trying to specify? So on the left-hand side, you have a single three-way relationship connecting these three different entity sites. And this cover, what you are trying to say is actually this type constraint and nothing else, right? And on the right-hand side, what are you trying to say here? Well, I have three different binary relationships, right? So essentially what you are saying is, okay, so I'm saying these three different sentences, right, by drawing the diagram on the right-hand side. For each of this binary relationship is corresponding to like essentially one logical sentence about the type constraint. So this is all I'm saying by drawing these two things. And clearly, if you translate them into this logical system, it's very clear to see that they are actually not equivalent in the sense that you can actually very easily construct a database instance that satisfies the logical formula on the left-hand side, but does not satisfy the logical formula on the right-hand side or vice versa. So this is actually one way to think about entity relationship diagram. It's not something that vague, not something that imprecise. It's actually have a very precise and formal foundation underneath the cover. So another concept that we are going to introduce in entity relationship diagram is something that we call cardinality. Okay, so it's actually try to model something that we don't know how to model at this moment. That is assuming we have these two entity sites, professor and course, and we have one relationship, for example, teaches, right? Professor teaches course, right? Connecting these two entity sites. And assuming this application, I want to encode something to say, yeah, one professor only teach one course per semester, right? So how can I do that? So far, given all the concepts we have introduced, I mean, there's no way you can do that because I cannot constrain how many relationships that one entity can participate in, right? So we never define that, right? So, and that's actually give you some motivation about defining a new concept that we are going to call cardinality. And it's probably one of the most tricky concepts in entity-relationship diagram. Essentially tell you how many times a given entity can participate in one relationship. So there are multiple types of things you can define here. So you can define a relationship to be a one-to-many relationship, which means that if you have entity site A participate in a one-to-many relationship with another entity site B, it means that for any entity A, it can have relationship with multiple B entities. However, on the other hand, for a single B entity, it can only participate in one relationship with any of those A entities. So essentially, right, if I say A participate in a one-to-many relationship with B, it actually means that on the left-hand side, you have a whole bunch of entity in any set A. On the right-hand side, you have a whole bunch of B entities, right? You cannot have like this link, right? So single A entity can participate in multiple relationship with B, but a single B entity can only participate in one relationship with entity in A. You cannot have this single entity in B have a relationship with multiple with multiple entities in A, right? If you say, yeah, so A participates in one-to-many relationship, essentially you cannot have this link. So how to draw this inside the ER diagram, right? So the way that you draw it is there are multiple ways you can do it. We are going to talk about the second way on Wednesday, but today, right? So you can actually have this one and n notation, right? If A participate in a one-to-many relationship, right? You write one, right, in the one part, and you write n in the multiple part, like in the many part, right? So if you have this one and n notation, right, essentially you are saying that, okay, so this relationship R is a one-to-many relationship, right? And A is the one part, B is the many part. It means that a single A can participate in multiple of this relationship, but a single B can only participate once in this relationship. So given this notation, if you want to encode information that one professor can only teach one course per semester, essentially what we are having is, okay, so there's this one-to-many relationship between course and professor, right? You have the one for the course and the many for the professor, which means that a course can participate multiple times in this relationship, but a single professor can only participate once in this relationship. That is, one professor can only teach one course, right? But of course, the same course can be taught by different professors. Right? So that is what you are trying to say by having this notation. And then there's the other way around, right? So given the same thing, right? So if I want to have, say, yeah, so one course can only be taught by one professor, what should I do, right? So there's the other side of the one-to-many relationship, called the many-to-one relationship, right? So if any side A participate in a many-to-one relationship with B, it actually means the other way around. That is, a single B entity, right, can have relationship with multiple A entities, but a single A entity can only have relationship with only one B entity, right? To draw this in a graphical way, right, you have a whole bunch of A entity on the left-hand side, have a whole bunch of B entity on the right-hand side, right? If I say there's a many-to-one relationship, right, from A to B, it actually means that you cannot have this link between A and B. That is, for any single A entity, this orange circle, it can only participate in this relationship once. Okay, so again, we can use this one to like one n like notation to actually put it here. If I have the n here, the many here, and the one here, right? So essentially, there's a many to one, right? N is many, one is one. Okay, many to one relationship between A and B. Okay, so and you can actually use this notation to put in the diagram on the like above to say, yeah, if I put n here with a course and the one is a professor, right? There's a many to one relationship between course and professor, right? In this case, like essentially one course can only be taught by one professor. And you can have another type of cardinality. For example, you say, yeah, so what if in my application, one course can only be taught by one professor, while one professor can only teach one course. Right? So in this case, there's another type of cardinality called a one-to-one relationship. right? If entity set A participates in a one-to-one relationship with B, it means that for entity A, it can only have one relation with B. For entity B, it can only have one relation with only one entity A, right? So in this case, essentially, there's this one-to-one mapping between these two entity sites. You cannot have a link that looks like this, that break it. So in this case, you use the one-to-one notation. The thing you're going to have is, okay, so there's a one-to-one relationship between these two entity sites. I have the one here, and also I can also put one here, which means that, okay, the relationship R is one-to-one, okay, between A and B. Okay. You can also write something like this. It actually means that one professor can only participate once in this relationship, and also one course can also participate once in this relationship. The consequence of this is one professor can only teach one course, and one course can only be taught by one professor. Okay, so this is how to specify cardinality. So another thing is there's another relationship called the many-to-many relationship, right? Which pretty much do not constrain anything, right? If you draw nothing here, you are specifying a many-to-many relationship that's one entity A can participate multiple times, and also one entity B can also participate like multiple times. You are allowing pretty much like everything between this like two entity sites, right? So if you draw nothing, right, by default, you are having this many-to-many relationship, but in principle, you can also put like N here, right? And you say, yeah, this many-to-many. So there's one question in the chat window. Shouldn't we add direction to edges in the diagram when we connect entity relationship? Yeah, so there are multiple ways for you to draw this, okay? So you can actually add those like arrow, right? Like direction in edges to specify many-to-one or one-to-many, right? So here the notation that we have is you can actually label this edge with either one or n. Okay, so I mean, there's no, I mean, these are just two different ways for you to specify the same thing. Okay, but in this course, we are assuming you are using this notation. Okay, make sense? Did I answer your question? Okay. No, it's not implicit, right? So there's like two different notations, right? So you can specify this like one-to-many using direction in edges. You can also specify the same thing by label the edge with one and n, right? I mean, just two different notations to specify the same thing. Yeah. Okay, great. Okay, so this notation can be slightly confusing, but it's actually not that confusing when you go to the formal semantics about what we are actually talking about. So this becomes a little bit confusing when you have those multi-way relationship, right? So assuming you have this four-way relationship R between four entity sites A, B, C, and D, and I have this cardinality label 1, 1, n here, right? What do we really mean by that? So essentially, formally, what do we mean is for every single one in the diagram, you actually introduce one first-order logic constraint, okay? Which means that for every single one, right, if you look at this thing, if you look at this one, right, it actually tells you that, okay, in this model, if you gave me a unique value of B, C, and D, like for the rest of the things, I can uniquely identify a single attribute in A. So that's actually what this one tries to tell you in cardinality, okay? And also for this one, right, it actually tells you, okay, if you give me a unique value of A, B, and D, I can uniquely identify this value C, okay? When you have this cardinality notation by labeling the edge with 1 and n, right, this is actually what you are trying to say. So formally, right, so actually this is something that's easier to understand if you write down a formal thing. That is, for every single one label inside the ER diagram, you are introducing one essentially like logical sentence. for the first thing, you are saying that, okay, if you give me like one tuple, right? XA, XB, XC, XD in this relationship, it means that it actually implies there does not exist another participation between XA prime, XB, XC, XC. That is, you have the same value for B, C, and D, but you have a different value for A. Okay, so this one here corresponding to this logical sentence. Okay, formally, that's what it means. And for the other one, for this thing, right, it's actually corresponding to this logical sentence. That is, as long as I have the participation XA, XB, XC, XD, right, in this R, I do not allow another participation with the same A, B, and D value, but have a different C value. Okay, formally, when you have this 1 and n notation, this is what you mean. For every single edge is being labeled by 1, you introduce this logical formula. Okay, and all the database instances that you are allowing in this model need to satisfy these two different sentences because you have two edges being labeled as 1. Okay. So intuitively, what does this mean? It means that if you draw this diagram, if I know the value of A, B, and D, I know which C uniquely is participating in this relationship. If I know the value of B, C, and D, I know uniquely which A is participate in this relationship. So that is what we mean by this. Now let's look at some example, right? So if we have this diagram, you have 3 different entity sites, student, professor, and topic, and you have a relationship R connecting this. And my connect label will look like this. Student edge is N, right? Professor is 1, and this topic is 1. So what do I mean by this? I mean 2 things. That is, in this kind of a relationship, right? So if I know the student and the professor, okay, I can uniquely tell you which topic participate in this relationship. Okay, I cannot have the same student and professor being associated with multiple topics. Okay, that is what this means. Like this one try to tell you. Another thing that we are trying to say from this diagram is if you tell me uniquely a student topic, it can be only associated with one professor. Okay, this is what this one try to tell you. Okay, so now let's look at some examples. Because when we talk about ER model, we are actually trying to specify the type of database instance we are allowing here. And go back to the formal semantic. Assuming I have this diagram, have this 2, 1 label for these 2 edges, is this database instance possible? I have 2 participations for this relationship R. I have student 1, professor 1, topic 1. Okay, and have student 1, professor 1, topic 2. Are we allowing this database instance for this application if I have a ER diagram on the right-hand side? So in this case, actually no, right? Why? Because this actually breaks the kinetic constraint, right? You have student 1, professor 1, student 1, professor 1, they're actually being associated with different topics, right? So that's not possible because I have this 1 here, right? Actually saying that you cannot have the same professor and student pair being associated with different topics, okay? So because of that, I'm actually not allowing like this database instance in this application. So how about this one? I have student 1, professor 1, topic 1, student 1, professor 2, topic 1. Are we allowing this? The way to think about it is to say, yeah, let's try to go through every single constraint I have to see whether it satisfies or not. So if we take this topic thing, right? So what I'm saying is, I cannot have different topic associated with the same professor and student pair. In this case, it is actually okay because these two are actually two different pairs, right? So it won't like break the topic constraint, right? So, and then I look at this second thing associated with professor. It means that if I know the student and topic, I can uniquely identify a professor, right? So that's what that kinetic constraint try to tell you. In this case, if I know a student and topic, right? These two are the same pair, but in this case, they are actually associated with a different professor, right? So in this case, clearly we do not allow this inside our database because that breaks this second kinetic constraint. How about this one? Right? You have student one, professor one, topic one, student one, professor two, topic two. So again, right, the way to think about this is you go through all the kinetic constraints and you try to see whether it's violated or not. If you look at the kinetic constraint about this topic thing, right, this one, it means that you have student and professor, a unique identified topic. In this case, right, the student and professor pair are different, right? So then this kinetic constraint will actually always be satisfied, right? So you cannot have, you cannot find in this database the same student professor value correspond to different topics. So it's fine. You look at this professor constraint, right? Essentially say, if you give me a unique student and topic, I can identify a professor, right? So in this case, the student and topic pair are actually different. This is student one, topic one, student one, topic two. This pair is different, right? So then each one of them uniquely identify professor. Student one and topic one go to professor one. Student one, topic two go to professor two. So it's okay. Okay. So under this model, the third database instance, right, on the left-hand side, is something that you are allowed, like in this application. So similarly, right, so you can go to this one, right, to see whether this is allowed under your model. You have student one, professor one, topic one, student two, professor one, topic one, right? So again, right, the way to think about this is very systematic. You go through every single kinetic constraint, right? And then essentially for the topic, right, you can say, yeah, so for student one, professor one, I uniquely identify topic one, right? Student two, professor one, I go to topic one, so it's fun, right? So different pair, right? So there's, yeah, so it's fun. If you go to the professor part, right, it's also fun, right? Student one, topic one, go to professor one, student two, topic one, go to professor, so it's fun. In this case, right? So this is also a database instance that is allowed under this model. So any questions here? So cardinality can be a little bit confusing, right? So but the way to think about it is, at least in the beginning, right, to go back to the formal semantic. Okay, so for every single one label, for every single edge, you introduce a logical formula to say, if I know the rest of the entity, I can uniquely identify like this entity. Okay, so formally, that's what it is. Any questions? If you have any questions, just raise your hand or type things in the chat window, right? It's very important to get cardinality right, right? So it's one of the most confusing concept for ER diagram. Okay, great. Yeah. Now, once we have cardinality, let's try to understand this diagram. Let's read that together, okay? So now I have this 1 and n notation to specify cardinality. What does this tell me? Let's try to read, for example, one relationship. Let's try to read this a tens relation, okay? What does this tell me? Essentially, right, so what is the kinetic constraint? Right, the student side is n, right? So this is not 1, right? So essentially, that we are saying that, yeah, I mean, this case, it's a many-to-many relationship between students and lecturer. Okay, in this case, it means that one student can attend multiple lectures, and one lecturer can have multiple students. Okay, and then you can have this requires relationship. Let's look at this. Again, this is N, this is M, there's no one there, right? So this is a many-to-many relationship, right? So essentially means that one lecture can require multiple other lectures, and one lecture can have prerequisite from multiple lectures. So now let's look at this Gibbs relationship, right? Professor gives lecture. So in this case, you can see here is N, right? Here is 1, right? So in this case, what does it tell you? It tells you that, again, go back to the formal semantic. You look at the one side, because that is the constraint that you are introducing. It actually means that if you give me the lecture, I can uniquely identify professor. I cannot have two, so that I cannot have one lecture associated with two different professors. Okay, makes sense? Like one lecture can be taught by only one professor. So that is what this one try to tell you. Okay, and then you can go to, for example, the works for relationship between assistant and professor, right? In this case, you have N here, you have 1 here. What does it tell you? This tells you that if I know the assistant, I can identify a professor. Okay, in this case, you cannot have one assistant on the left-hand side associated with two different professors. That's what this one try to tell you. Now let's look at this three-way relationship between student, lecturer, and the professor. Okay, so in this case, again, try to read it by looking at all the ones here, right? It means that if you give me a unique value of student and lecturer, I can specify the professor side, right? That is, if you give me a pair of student and lecturer, right, there's only one professor that pair can associate with. Okay, makes sense? So this is actually the kinetic constraint inside this example. And what do they mean, right? So this is all about entity relationship diagram, right? So and in practice, right? So the when you find a real job and try to draw one of those diagrams, so there are a lot of those very interesting tools that you can actually use to help you to actually draw those diagrams, right? So let's just use one of these tools and try to go through a very simple process, right? Of kind of conceptually modeling some application. Right, so in this on the left-hand side, assuming you want to build the next generation of digitech, for example, right? So yeah, I need to store the data somewhere, right? How can we model that? What are the data that we need to introduce, right, in this database, right? One thing that you could do is, okay, so if you look at this, right? So there's all those product, right? So here are the different type of laptops, right? So one thing that I could say is, okay, maybe let's have one entity side corresponding to all the possible, for example, notebooks, right? So thing you can do is, in many of the tools, you can say, yeah, let's click this and we can introduce one entity, right? So, and this entity side is, for example, notebook, a whole bunch of notebooks, right? So, and then you can have different attributes associated with this notebook. For example, you can have one of these attributes, for example, the keyboard layout, for example, right? You can actually say, yeah. So in this tool, you can say, yeah, so I also have some attributes. This attribute is my keyboard layout. And then you can actually connect these two things. In this case, you can actually say, yeah, let's connect this. Okay. Yeah, you can actually draw this. You can say, yeah, so from this diagram, I have a whole bunch of entities corresponding to notebook. Each notebook corresponding to have attribute keyboard layout, right? You can have, say, yeah, I can have different, for example, the processor family, right? So in this case, I mean, you have different things, you can do different things. For example, you can say, yeah, you can model this as the attributes, right? Or you can also model this as entity. Right? So you can say, yeah, I have different type of processor, right? And for each processor, for example, you have some attributes associated with this processor. So let's say maybe that is the vendor, for example, there's Apple, there's Intel, for example, right? And you can say, yeah, so one notebook can be associated with one and only one processor, right? For example, in this case, you can say, yeah, so these are the two different entity sites. I can actually have one relationship and I will try to connect them, right? So you can say, yeah, maybe the relationship is a task processor, right? And that's going to connect these two different entity sites. Yeah, and you can introduce, for example, kinetic constraint between this. Okay, you can say, yeah, there's a many-to-one relationship between these two, right? So in this case, you can see it's actually using a slightly different notation for this many-to-one thing. Okay, so in practice, there are many different ways people can specify this many-to-one relationship. Okay, so in this course, we have this one and n notation. In practice, there could be actually many other different ways for you to specify the same thing. Okay, so in practice, people will not draw this diagram on a piece of paper. What's going to happen is all those automatic tools, not automatic, but all those kind of tools for you to specify such a diagram. So good thing about this is, as we are going to see in the next lecture, is once you have this entity relationship diagram inside this type of tools, they can also semi-automatically generate a relational schema for you and also generate a whole bunch of SQL queries that you can actually run inside your database to create such a schema. Okay, so if you're interested in this, right, you can just Google like ER diagram on the internet. You can find a whole bunch of these tools, and you can actually try to play with them. Okay, so that's all we have for today, right? So in the next lecture, we are going to talk about actually some other property, like some other things you can do in ER diagram. And also we are going to talk about how to take as input an entity relationship diagram and map them into a relational model schema. Okay, so that's all for today. So the next lecture will be hybrid. I will be in the classroom. And if you have any questions today, I'll be here to answer them. Otherwise, I'll see you guys on Wednesday. Yeah, if you have any questions, just speak out. Yeah, I'll be here. Okay, so if there's no question, I'll see you guys on Wednesday.